Now we're going to talk about free fall. Aristotle, back in the 300s BC, contributed greatly to the beginnings of physics. And what he said was that if you had a heavy object and a light object, that heavy object would fall faster than the lighter object. And for 2,000 years, his idea stood firm until Galileo started working and thinking through this. And he said that as long as air resistance was the same, both should fall at the same rate. And it turned out that he was correct. So when we talk about free fall, we talk about an object that's falling where it's not impeded, it's unimpeded, meaning that it's not encountering another object. And so gravity is accelerating all objects to the center of the Earth when it's in free fall. The entire time it rises as well as when it falls. And this is a little bit of a strange idea that we're going to unpack. The acceleration during that entire time period is negative 9.8 meters per second squared. And so as the object goes up and as the object falls. And it's always towards the center of the Earth, and it's constant. And we're going to work through that. What we're going to do is also ignore air resistance for this time period. And so we're going to assume that there's no terminal velocity, there's no air resistance. And so it's the acceleration will stay at negative 9.8 meters per second squared. So if we were to illustrate this, this is an important thing that you probably want to draw with me as we do this. Let's say our initial velocity of our object was 39.2, positive 39.2 meters per second. And we're throwing this ball into the air. We know that the acceleration is negative 9.8 meters per second squared. It stays that the whole time. Now, if you remember from earlier, we said that acceleration is the change in velocity every second. So if the change in velocity every second would be in free fall, negative 9.8, that means we would take out 9.8 from this because the velocity is going up, but the acceleration is down. And so what we would get here is after a second, the velocity would be 29.4. So, oh, I drew that here. Okay, 29.4 meters per second. Okay. Now, after the next second, another change, right? This is the change in velocity every second. It's going to get 9.8 meters per second slower. So now it's 19.6, positive 19.6 meters per second. And then after the next second, it's going to be 9.8 meters per second slower. And now it's only, the velocity is actually 9.8 meters per second. And then after that, after the next second, it's actually 0 meters per second at the top. And you can see this if you take an object and you throw it into the air. You'll see that at the top, it's not going up anymore, but it hasn't started going down yet. And so for that split second, it's 0. And then after another second, again, this is the change in velocity every second. It's going to start to come back down, and after another second, it's going to be negative 9.8 meters per second. And then after another second, it's going to be, again, the change here. It's going to be going negative 19.6 meters per second. And after the next second, it's going to be going negative 29.4. And after the final second there, it's actually going to be the exact same, 39.2 meters per second, but the velocity is equal and opposite to what it was when it started. And that will always be true. And that's an important thing to see here. So when something is throwing up, or when you're throwing an object into the air, it's going to be symmetric. It's going to spend half the time going up, the other half going down. And when the velocity, or when the object comes back down, the velocity is going to be equal and opposite to what it was when it started. And again, acceleration both on the way up and on the way down was negative 9.8, and hopefully that illustration was helpful for you there. Okay, so we're going to try a problem-solving situation with this. We can go ahead and draw this. Here we've got a person, definitely not to scale. Okay, we're 120 meters high. So the initial position is 120 meters. The final position is 0 meters. And we're dropping it from rest. So the initial velocity is 0. And we want to find out how long is the ball in the air, how much time. So we know it's in free fall, so the acceleration is negative 9.8 meters per second squared. So if you look at your equation sheet, there's going to be something, or one of those that's going to give you time. Now, something that's commonly asked during this lesson is, well, can't we write down what the final velocity is down here? And thinking that it's 0, but it's actually not, because right before it hits the ground, it's going to be going pretty fast. As soon as it hits the ground, it's no longer in free fall. So this is really the only information that we know so far. Let's go ahead and do this as well. The final position minus the initial position. The final position is 0. The initial position is 120. So the actual displacement is negative 120 meters. So go ahead and pause the clip here and see if you can find which equation to use to find out the time, and go ahead and calculate that, and then continue from there. So go ahead and pause and then give that a try. Okay, so we should get 4.95 seconds as our time that it goes down. If you notice, this notation is just slightly different. This is the same, delta x equals v initial times time plus 1/2 at squared. And the displacement was negative 120. The velocity initial was 0. Acceleration is negative 9.8. And our only unknown is time. So that's the time. Now what I want you to try is to figure out what is the ball's speed and velocity when it strikes the ground. So now you are going to try to find VF. And so go ahead and pause the clip here and see if you can solve for the final velocity using one of those equations. Okay, so this is one way to find it. You could have used the final velocity equals the initial velocity squared, or final velocity squared equals initial velocity squared plus 2a delta x. Or, this is probably more likely, you use this one, final velocity equals initial velocity plus acceleration times time. So the initial velocity being 0, the acceleration is negative 9.8, the time is 4.95 seconds, and you would have gotten negative 48.497, or close to that, negative 48.5, if you use this rounded number. So if you notice, this actually does give you the velocity here, because it's got the negative. If you use this one, there's no negative there, so you have to be real careful. You have to recognize that the velocity is negative because it's going downwards. So when you have your final answer, you can describe it as 48.495 downward, or if you want to put a negative in front of that, you can as well. And so this is going to be important to recognize that. Now the speed, that's the velocity. The speed, remember, speed has no direction, so just plain 48.5. Now we can find what the speed and velocity is halfway. So now x initial would be 120, x final would be 60 meters. So go ahead and pause the clip here and see if you can solve for what the speed would be and the velocity would be halfway. And you can write down the other givens there as well. Okay, so in this case, if you solve for that, we would get 34.3 meters per second downward. And you couldn't really use time there because time wouldn't be half the amount of time, because this is a squared relationship. And then if we were to draw the graphs, the position time, velocity time, acceleration time, we can do that together. Position and time, it's getting faster and faster and faster as it goes down, so the slope gets steeper and steeper. The velocity starts from rest but gets faster in the negative. And then the acceleration here, it's kind of hard to see, is constant at negative 9.8. It's not changing. Okay, so this one, if we throw a ball straight up into the air, and we have a positive velocity of 20 meters per second, we want to find out how long is the ball in the air. So if the ball goes all the way to the top, we know at the top the velocity would be 0 at the top. So if we want to, we can set this up to where we can find the time that it takes to go all the way to the top, and then multiply that by 2, because we know that the time that it takes to go to the top will be the same amount of time that it takes to go to the bottom. So go ahead and pause the clip and see if you can solve for that. Okay. Okay, so we're looking again for the time. We've got the acceleration, we have the initial velocity, and if it's 0 at the top, we can solve for it, and we'd end up getting 2.04 seconds. Now that's the time only halfway. So we would have to multiply that by 2, so the total time it would take to go all the way up, all the way down would be 4.08 seconds. Now the second part of this, how high does the ball go? That is delta x. How high does it go? So why don't you go ahead and try this. We know the initial velocity again is positive 20. And there's a couple different ways to do this. Why don't you go ahead and try this and see if you can get it, and then go from there. So go ahead and pause it and then play when you're ready. Okay, so this would be using the velocity of being 0 at the top. The initial velocity is 20 at the bottom. So we would get 20.41 meters as the displacement. Now you could have done this. You could have set it up to the displacement equals v initial times time plus 1/2 at squared. Now if you did that, you would have to recognize that you're using this time, because how much time is it to go to the top? It's only 2.04 seconds to the top. So when you're multiplying 20, it would have to be multiplied by 2.04. And then we would have 1/2 times negative 9.8 times 2.04 squared. And then you should get the same thing.